Welcome to online training session, day 7, Topology and Combination Optimization. So, we'll see about the training series details. Till date we have covered the day 1, that is FEM theory, day 2 1D meshing, day 3 2D meshing, day 4 3D meshing, day 5 I have divided into 3 different parts for the analysis and post-processing. Day 6 I have divided into 2 parts for the topology optimization, and earlier it was the composite and combination optimization is on day 10, but as for the time availability I have combined them with a day 7, that is topography optimization plus composite and combination optimization. Later on the next sessions will be on size optimization and shape optimization. So the topics which I am going to cover in today's training session are as follows. First we will see topography optimization of a plate under torsion, then topography optimization of a L bracket, automatic recognition of bead results from topography optimization of an L bracket, then random response optimization, combined topology and topography optimization of a slider suspension, then optimization driven design of a composite aircraft underbelly fairing. So let's see the problem definition for the first tutorial, that is topography optimization of a plate under torsion. In this tutorial, demonstrate how to perform topography optimization of a plate under torsion. A finite element model of a design space with loads and constraints applied is shown in the below image, as you can see here. It is assumed that the part is to be formed using a stamping process. The objective is to minimize the displacement of the node where the force is applied in positive z direction. So we are going to reduce the displacement. That's my objective for this topography optimization processes. That is, z direction displacement should be minimized. Only the shape of the plate can be changed to achieve the objective, not the thickness. So we will create topography optimization help us to create the bead pattern. So with the help of bead patterns, we can increase the stiffness of the components. So a finite element model, as shown in the below figure, is loaded into hypermesh. The constraints, load, material properties, and subcases, that is the load step of the model, is already defined. Topography designs variables and optimization parameters are defined, and the OptiStruct software is used to determine the optimal reinforcement pattern. The results are viewed as animation of contours of the shape changes of the design space. Finally, the use of grouping pattern is shown based on the shape change suggested by OptiStruct. A possible pattern is chosen for ease of manufacturing. So bead patterns will go to different manufacturing constraints, also see what are the constraints you can put to get a better bead patterns as per the manufacturability. The optimization problem for this tutorial is stated as: objective is to minimize the nodal displacement at a grid point where the load is applied, and my design variable is the shape variable generated automatically on the designable space aligned with the element's normal. The process covered in this tutorial includes setting up topography optimization in hypermesh, post-processing topology optimization results, including a manufacturing constraints in optimization process. So let's start with opening of hypermesh. So go to Start All Programs, HyperWorks 12 Student Edition, and click on HyperWorks. So it will open a GUI something like this. If you are using HyperWorks 11 version, this is 12 as you can see at the top. If you are using HyperWorks 11 version, then it will come as radius, bulk data. But if you are using HyperWorks 12 version, you can select OptiStruct as the user profile. Both are the same for static analysis and optimization. So click OK. Once you click OK, and after selecting the user profile as OptiStruct and click OK, you will see the it will generate the templates regarding the OptiStruct solver. So in this way, my user profile is loaded. At the top, you can see the OptiStruct as a user profile has been loaded. So let's open the model in HyperWorks Student Edition. So go to Open, browse the file where you have saved. This is my plate. on which I am going to see the topography optimization process. So as I have already mentioned that the material property component, load collectors and load step is already defined. Now we'll start with defining the topography optimization. So before that, let's see the thickness of the component. So click on the, just move it to here. You can move these panels from this to this side. So click on the property icon as given here. Click on update, select the property, click on update edit and check the thickness. So the thickness is 1. Currently the component thickness is 1 mm. Now let's start up with setting up the topography optimization in HyperMesh. So the first step is define design variable for topography optimization. So for the topography optimization, a design space and a bead definition need to be defined. The following section outlines how this can be done. For further information on bead definition, please see the reference manual on the DTPG card. So we'll go to analysis page to define the design variable. We'll go to analysis page optimization. I'll again highlight it. Go to analysis page optimization. In optimization, select topography panel. Select topography. Enter the design variable name, let's suppose topo. Select the property which you want to take in the design space. So as I have only one property, so I'll select that. And click on create. So my design variable is created now, as you can see. So a topography design space topo has been created. All elements organized in the design component collector are now included in the design space. Now select bead params. So to define the bead parameters, select bead params. Click on the DSVR, that is design variable, and select the design variable topo which we have created in the previous step. Enter minimum width as 5. So this parameter controls this parameter controls the width of the beads in the model. The recommended value is between 1.5 to 2.5 times the average element width. That is the width of the bead it will generate. Like let's suppose it generates the width something like this. So the width of the bead patterns will be 5 mm. So the minimum width will be 5 mm. It will not be less than that. So you can put it like that. Then the next is the draw angle. Enter the draw angle as 60. So this parameter controls the angle of the side of the bead. The recommended value is between 60 to 75 degrees. So draw angle means if it creates a bead something like this, so the angle here will be 60 degrees. So it will be not more than that, because if it's a 90 degree, it will create a sharp corner. So this should not happen because it will get failed in this if it's a sharp corner. So that's why draw angle is important. Then a draw height, will enter the draw height as 4. So this parameter sets excuse me. This parameter sets the maximum height of the bead to be drawn. So draw height means if the bead will get generated, the height from the base will be 4 mm, will be the draw height. So these are the parameters which I have added. These are not manufacturing parameters, these are the general parameters for the bead generation. Then check the box next to buffer zone. So this parameter establishes a buffer zone between the elements in the design domain and elements outside the design domain. Make sure the draw direction is toggled to set to normal elements, draw direction set to normal elements, and make sure the boundary skip is set to load and SPC. So it will not create the beads where the loads and SPC are applied. So it will not create the beads on the nodes where the loads and SPC is applied. So make sure it load and SPC. So this tells the OptiStruct to leave the nodes at which loads or constraints are applied out of the design space. Then click on update. Make sure you click on update because most of the time people just get forgot to click on update and they get means not a good result because they didn't updated these parameters. Then select the bound sub panel using the radio button. This bound. Ensure that the topology design variable is selected, that topo. Upper bound enter the value as 1 and lower bound enter the value as 0 and click on update. So upper bound on variable controls grid movement, that is the real value is greater than the lowest bound, default value is 1. This sets the upper bound on grid movement equal to upper bound multiplied by highest grid thickness. Then click return to go back to the optimization panel. Now the next step is to define responses. So click on responses panel, that is on the third column first row. Enter the response name as displacement or say displace. Enter the response type as static displacement. Select the node where we want the displacement to be controlled. So on this, the location of the force, we want to minimize the displacement in degree of freedom 3, that is translation along z-axis. And click create. So my response is defined. Then the next step is to define the objective. So my objective is to minimize the response. So select the response as displacement. Click on the load step and select the load step which is created for the static analysis. And click on create. So on the model browser you can see the objective is also got created. Now save this file and run the analysis. So go to save as model. In desktop I will create a new folder. And in this I will create tutorial 1. And in tutorial 1, the case 1, where I haven't given any manufacturing constraints. So I have saved this file. Then go to analysis page, OptiStruct to solve it. Export option to all, run option to an optimization, memory keep as default, and click on OptiStruct. So it will start the optimization solution. This is the solver window where it will solve for the different iterations as per my requirement. So now as you can see, my optimization has converged and feasible design, all constraints are satisfied. So just click on results to see the results. I'll just close the solver window. This is just the message log, not the error. Select last iteration, that is 20 seconds. Go to contour icon. Select the result shape change. So it will show you from 0 to 4 the thickness, the bead pattern. So blue are in the 0, red is on 4 mm height. So this will be the bead patterns to minimize the displacement. Now we will see how much displacement is minimized. That is also important to see. So to see the value of how much displacement is minimized, I'll split the window into two. Click on the second window. Go to open folder. In this, I will select torsion plate s1.x3d file that contains the result, subcase 1. Select 0 iteration and say apply. So this is the displacement for the 0th iteration. I will check the maximum value. So this is the maximum value for the 0th iteration. And for the 22nd iteration, my maximum value is coming to be 4.46 at the same node 2500. So when the beads are not created, the displacement is coming as 39, but after creating a bead, the displacement is lowering down to 4.4. But as per the manufacturability issues, that's what I think, this component is not so much manufacturable. So I will add some manufacturing constraint to get a proper bead patterns which are more manufacturable. So I will close this session. In Hypermesh, again I will go to Analysis, Optimization and click on Topography. This time I will select Pattern Grouping. So pattern grouping allows me to create a manufacturing constraints. So I will select the pattern type as linear. Select the anchor node as this node and the first node as this to define the axis to generate the pattern. So perpendicular to this axis it will create a bead, something like this. I will highlight it. So it will now create a bead something like this. So from this to this, at certain locations it will create a bead. Select the subtype as basic and click on update. Just we will update the manufacturing constraints. Again save the file as case 2. Analysis, OptiStruct. I will increase the memory size, let's suppose 1000 MB and click on OptiStruct. So increasing the memory option in MB will increase the solver time, will decrease the solver time. So my solver has started. So now as you can see, my analysis is now completed. So I will click on results to view the results. Select the last iteration Go to contour, apply. I haven't changed anything, but you can see just by applying the manufacturing constraint, the bead patterns are more manufacturable. So it generates a proper bead pattern, but it may differ the displacement value because I haven't constrained the displacement value. I just asked to minimize it. So minimizing the displacement value means below 39 any will be get a minimized value. So if you want to constrain, you can use deconstraint to constrain the minimum displacement value. So in this way you can use topography optimization to create a bead pattern. You can also see the displacement for that. Now let's move to the next tutorial, that is topography optimization of L bracket. This tutorial focuses on topography optimization of L bracket modeled with an attached mesh. The bracket is modeled with shell mesh. The objective is to maximize the frequency of the first mode by introducing beads or swedges to the bracket. This can be achieved by using topography optimization. The model is shown in the figure below. The region around the holes are specified as non-designable, while the bulk of the bracket is available for developing the stiffening beads. The optimization problem for this tutorial is stated as the objective is to maximize the first frequency. My constraint is bead dimensions and layout. My design variable is perturbation of nodes normal to shell mid plane. The following processes are included in this tutorial: setting up a topography optimization in HyperMesh, post process the results in topography optimization. So I will open HyperWorks Student Edition, browse the file, second tutorial. So this is my L bracket, as you can see. So the whole areas are the non-designable. I will not create the beads around these whole patterns. Rest I can go for the design variable. So my component, load collectors, load step, material properties defined. I define two properties because there are two different components. One is design, one is fixed as the non-design. So let's start by setting up topography optimization in HyperMesh. So go to analysis, optimization, topography. Select the radio button as create. Enter the design variable name. Let's say again I'll enter topography. You can enter whatever you want. Select the property which you want to take in the optimization. So I want to take the property of design in the optimization process. So I'll only select the design as the property and click on create. So my design variable is created, as you can see. Then the next step is to define the bead params, that is bead parameters. So I will select the topo G, enter the minimum width to be 15. Draw angle, I will put it as 85. I will enter the height, let's say 5. It's a permutation and combination. Check the buffer zone box, elements to normal. Skip the loads and SPC and click on update. Then we will select pattern grouping. Select the pattern type as one plane symmetry. Select the anchor node as the center one, that is this one, and the other one is the straight to this, that is 1613. So perpendicular to this plane, this is the axis, perpendicular to this plane, it will create a symmetric bead pattern. Click on update. Go to bounds. Enter the upper bound value as 1, keep it as default, lower bound value as 0, and click update. So I have updated the topography optimization design variable. Then my next step is to create responses. I will create the response. Enter the response name as frequency. Response type as frequency. select the switch below response type and frequency, then the number of modes will be 1 and click on create. So first mode I want to maximize the frequency. Then click return to go back to the main menu. So now my objective I will define. My objective is to maximize frequency, the first mode, and click create. So my objective is also defined. Now I will save this file, click return, again click return, go to file, save as model, and save this. Go to analysis, OptiStruct, run option to all, export option to all, run option to optimization. Keep the memory as 1000 if you have sufficient memory on your RAM memory on your machine. Click on OptiStruct, it will start the solver. So the solver has started. So as now you can see, the optimization has converged and feasible design has achieved. So I will click on the results. So I'll just close the message log. This is not an error. This is a message log regarding the license files and all. So just close it. This is the first iteration. Go to the last iteration. Contour, shape change and apply. So it has created a bead up to a height of 5. The symmetric bead along this axis. So the whatever the bead pattern is on this side will be the same as the opposite side. Then split the window into 2 and see the whether it has changed the increases the maximum frequency or not. Open. In second tutorial, select S1 file. Press F. It is so high, so we'll just decrease its value. Then for the first iteration, I will on the maximum value, min max results. Eigenvolts, static min max. So the maximum value is 271 for the first iteration, and for the last it is 248. So it has increased the maximum frequency or the frequency for the first mode. So this is the first iteration, this is the last iteration. So in this way you can see the values for the maximum frequencies. Go to contour, apply, last iteration, apply. So you can see the frequencies for last iteration is 93 and for 0 it is 48. So it has increased the frequency for the first mode. So I'll close this window, click new. Then we'll move to the next tutorial, that is automatic recognition of beat results from topography optimization of L bracket. So the objective of this tutorial is to run the completed model from the previous tutorial post-process the result and use the bead functionality. The objective of AutoBead is to offer automation of bead interpretation so that prototype like design could be created automatically. So we'll create a surface file, that is the IGS file from this model. In this tutorial you will execute a topography optimization, post-process a topography results with Hyperview, generate a new model based on topography results. So we'll see how we can do it. So open the file for the third tutorial. I think this is the FEM file, so I will open the FEM file. So click on import, select the file type as OptiStruct, file, day 7, third tutorial, and click import. Keeping all the parameters as it is, just click on import. Close this. So you can see the design variable, the component, design variable, load collector, load step, material, objective, optimization response, property, everything is predefined. So what I'm going to do is, I'll save this file and run the analysis. We are not going to see the optimization process. We are going to see how to get the files from the optimization process. So I'll go to File, Save as Model. And save this as L bracket, analysis, OptiStruct, and solve it for the optimization. So it will start the solver window, as you can see. So my optimization has converged, so we'll view the results. So this is the last iteration with the shape change of the previous. So this is same as we did earlier. Now we will see how to get this model in Hypermesh again to do further analysis or modification. So go to post page. On post page, click on apply result. In simulate, select design 12, data type shape change, select displacement, keep total displacement, select nodes all, enter multi as this and say apply. So this is the result type which you can see. Click reject and return. In this way you can see the shape change in elemental forms in Hypermesh. That's the results, and if you want to use that result in the model, you can use it by apply results. And if you get the IGS file, if you want to get the deformed shape of the optimized shape, click on OS Smooth. Select the model file, go to desktop, new folder, FEM, select the SH file. In this you will find the SH file. If you want to get the grids, you can select the grid file. Select the threshold value as 0.3. Click all the other parameters as it is and click on OS Smooth. Again click on FE surface. So it will generate the surface using the elements which are in the shape change. So it smoothen the geometry. Earlier the beads are not so accurate, so it's just smoothen it. Click save and exit. So this is the geometry file. As you can see, if I close this, so I'll just change the color of this one to this and this one to this. Keep it as mixed. So it has smoothened it a bit. Rest you can do it if you want to smoothen it some more. There are some geometry options available through which you can smoothen it some more. So this is the optimized model or the geometry of the optimized shape. So in this way you can get the optimized shape of your optimization. So shape changes can also be bring it down. So you can save it to any format. Like if I want to save this as HM file, I'll go to model and save it as shape change. So I just saved it in HM format. If I want IGS, go to export geometry, IGS, go to desktop, new folder, third tutorial, L bracket, shape change, export option to displayed and click on export. So the geometry file has been exported. Click new. Import, we'll just check whether the shape is exported or not. So shape change, import. So the two components with the shape change. So the rest of the geometry editing is possible here. If you want, if you have the IGS file, so you can do the further modifications in the CAD software if you want, or also in this software. So you can create and toggle the surfaces or split lines which are not proper. So in this way you can just merge these lines. So in this way I have ended with this tutorial. I will click new. We'll move to the next tutorial, that is random response optimization. So a topography optimization with random response is performed on a flat plate in this tutorial. A random response analysis has been set up as shown in the following image. The flat plate is constrained through a RBE2 element. Two frequency varying accelerations are applied on the independent node of RBE2 element as excitation. They are correlated through a cross spectral density. The objective of the optimization is to minimize the maximum, that is mean max power spectral density, that is PSD acceleration in X direction at the center of the plate. The following sections are included: create a topography optimization with PSD response in Hypermesh, submit a job in OptiStruct, post-process the result in Hyperview and Hypergraph. So I'll open this model in Hypermesh. So desktop, Day 7, fourth tutorial. I think it's an FEM file. So import solver deck, OptiStruct, browse the file where the file you have saved and click on import. So in this way you can find this is the model with the components, load collector, load step, material and property. All are defined for this component. So we will create a random response optimization. The first step to create the random response optimization is to create a design variable for topography optimization. So in this exercise, the design space is composed of shell elements with a property pshell_5, this property. And minimum width of 0.4, a bead height of 1 and a draw angle of 60 degrees is used in the bead definition. A two-plane symmetrical pattern grouping constraint is defined to generate a symmetric bead design. I'll go to analysis page, click on optimization, select topography panel to define the topography design variable. Make sure the create radio button is selected. Enter the design variable name, let's suppose plate. Select the property which you want to take in the design space, as I want pshell_5 mm thick to be in the design space, and click create. Click on bead parameters, select the design variable as plate. Enter the minimum width as 0.4, draw angle will be 60 degree and draw height will be 1 mm. Check the buffer zone box, draw direction normal to elements, boundary skip regions none, and say update. So the design variable is updated now, as you can see. Then go to pattern grouping, select two plane symmetric pattern. Select the anchor node as coordinates, first node as coordinates, second node as coordinates. Anchor node as 0, 0, 0, first node as 0, 1, 0, and the second node is 0, 0, 1, and say update. So this will update the radio buttons, and go to bounds, upper bound as 1, lower bound as 0, and say update. So my design variable is generated. Now we will create a design response for random response optimization. So click return to go back to the optimization panel and click on responses. Enter the response name as PSD acceleration 1. Select the response type as PSD acceleration. Select the node, say by ID as 67. This node is the maximum where the power spectral density is seen during the basic base run. Select degree of freedom 1. Click on random response and select random response 100 as the load step which I have created. So which specify the power spectral density for the random response analysis. So keep all the frequency and no region tab as it is by default and click create. So now my objective response is defined. Then I will create the objective. So my objective is to minimize. First I will create an objective reference. So my objective reference, I will enter My design objective of a random response analysis is to minimize the maximum PSD acceleration at node 67. So first I have to define the objective reference. So I will enter objective reference value as PSD, acceleration reference, response as PSD acceleration, check the box next to negative reference, check the box next to positive reference, and in positive reference enter the value as 1.0 e to the power 6. So the value of response PSD acceleration will be normalized by the negative and positive reference value. Select all to apply the DOB objective reference entry to all the subcases. Click create. Then again click return. Then define objective, select mean max and select the objective reference. Click create. Click return twice to go back to the main menu. Save this file. I will enter the name as plate. Analysis, OptiStruct, keep all the other parameters as it is and click on OptiStruct to start the solver window. So my analysis process has started, as you can see. And a feasible design is achieved. So click on results to view the results. Select the last iteration. So these are the results. We'll view the power spectral density acceleration in hypergraph. So to switch it to hypergraph, click on this panel. Select hypergraph 2D. If you are not able to view this, go to view, toolbars, hyperworks, client selector. Make sure the client selector is checked. Select hypergraph 2D. Click on open folder and select the PCH file. Select the frequency in Hertz group first and apply. So this is the power spectral density change for the node number 67 or maximizing the minimum frequency. In the same way you can select for the second group. So they are overlapping each other. So in this way I have ended with this tutorial. I will close this window. Click new. So these are the tutorials for topography optimization. Let's move to the next tutorial, that is combined topology and topography optimization of slider suspension. So this tutorial performs a combined topology and topography optimization on a slider suspension using OptiStruct. The objective is to increase the stiffness of the slider suspension and make it lighter at the same time. This requires the use of both topography and topology optimization. The finite element model of a slider suspension contains force and boundary condition. The structure is made of quad element and has both linear static and normal mode subcases. Steps are described to define the topology and topography design space, responses, constraints and objective function. The optimized structure will be stiffer for both linear static and normal mode subcases and will have beads and less material. So the problem statement is perform combined topology and topography optimization on a disc-driven slider suspension to maximize the stiffness and weighted modes. The lower bound constraints on the 7th mode is 12 cycles per millisecond. My objective is to minimize the combined weighted compliances and the weighted modes. My constraint is the 7th mode should be greater than 12 cycles per millisecond. My design variable is element densities and node topography. So in this tutorial we will see how to set up a combined optimization using hypermesh, post-process the results in hyperview. So I'll open the HyperWorks Student Edition, browse the file, say import. Click close. So on the model browser you can see component, load collector, load step, material and properties already defined. So this is my model of the slider suspension, the force area where the forces is applied, and the other end is the constraint zone. So now we will start up with set up a topology design space. So to go to analysis page, optimization, click on topology, enter the name of the design variable, say topology, select the property as one pin, select the type as P shell because these are the shell elements, base thickness as 0 and click on create. Enter the design variable name, say bend, select the property as 3 bend, P shell and base thickness is 0 and say create. So I have created two design variable, one is pin, the other one is bend. Then select the topography design space. So click return and select topography. Make sure you are on the create radio button. Enter the design variable name, let's suppose topography. Click on the property and select pin 1 and 3 bend. Click create. So the design variable for topography is created. Select the bead parameters for topography. Enter the minimum width value as say 0.4. Draw angle to be 60 degree and draw height will be 15 mm. Buffer zone check. Normal to the elements, draw directions, skip boundaries, loads and SPC. And click on update. Select the pattern grouping. As one plane, nodes by ID, anchor as 41, first as 53. So perpendicular to this plane it will create a bead pattern symmetrically. So along this edge, so along this side and this side it will create a same bead pattern. Click update. Go to bounds. Upper bound as 1, lower bound as 0 and say update. Then create the responses. Go to response. Enter the response name as frequency. Select the response type as frequency. Assign the number of mode to be 7 and click create. Again click a response as combine. Change the response type as compliance index. Select the load step as force. Then enter the values of mode 1, weightage 0, 2, weightage 2, 3, 4, 5 and 6. Click create. So response has been defined. Then define the constraints. Response type as frequency. Lower bound limit is 12, it should not be below that for the frequency, and create. On the model browser you can see the constraint is defined, and objective, go to minimize the combined effect and check create. Now we'll define some optimization control cards. So I'll go to opti control. Check the box in front of minimum dimension and enter the value as 0.25. So minimum member size is generally recommended to avoid checkerboarding. It also ensures that the structure has the minimum dimension specified in this card. Click the box next to MATINIT and enter the value as 1. MATINIT declares the initial material fraction in the topology optimization. Material initial has several defaults based upon the following condition. If a mass is the objective function, then MATINIT default is 0.9. With constrained mass, the default is reset to the constrained value. If mass is not the objective function and it is not constrained, the default value is 0.6. Then click return. Again click return. We'll define some more cards to set up the mode tracking. So during optimization, the frequencies and their mode shapes may change order due to the change in element densities and other design changes. To overcome this, define a parameters to track the frequency so that only the intended frequencies are tracked during the optimization run. So click on control cards and select param. Check the box in front of mode track. Mode track. In mode V1 select yes, click return. So now the param button is green, so it is activated. Again click return to go back to the analysis page. Now I will save this file. Go to analysis, OptiStruct and click on OptiStruct to start the solver. So now as you can see, my optimization has converged and feasible design has achieved. So click on results to view the results. Select the last iteration, that is 27. Shape change apply. Go to ISO. Element densities, simple, and apply. So this is the area from where you can scoop out the material. If I change this, so this is the area from where you can scoop out the material. I'll enter it, say 0.3 or 0.5. So in this way you can remove the material as well as create the bead patterns. So both the things you can do simultaneously with the help of this. Element density, simple, and apply. So this is the element density ratio, element thickness, apply. So these are the different visualization things which you can see. So in this way I have ended with this tutorial. So I will close it. I will click new. So in this way I have ended with the online training session day 7, topography and combination optimization. Thank you very much for attending this training series. To improve the online training session, please help us by sharing your valuable comments at video-support@india.altia.com. And also, if you find something interesting regarding this training session, also please send your comments to encourage or to motivate us to generate some more training sessions like this. Thank you very much. If you need the files which I have used in this video, you can also write us the same at video-support@india.altia.com. I will definitely help you by providing the link from where you can download the files which I have used in this training session. Thank you very much. Have a great day. Bye from Apur Papad.